March 23, 1989, Salt Lake City, Utah. A room packed with journalists. Two scientists step up to the microphone and utter a phrase that makes physicists around the world hold their breath for a few seconds. They say they've achieved nuclear fusion in a beaker at room temperature. Not in a taka worth billions. Not at 100 million degrees, but an ordinary laboratory beaker with an electric current and a piece of metal immersed in water. They were Martin Fleischmann, a professor at the University of Southampton, a fellow of the Royal Society, and one of the world's leading electrochemists. And Stanley Pons, his American colleague, head of the chemistry department at the University of Utah. Both men of repute, both not charlatans, and both have just declared that, if confirmed, it will change everything. Friends, welcome to Fool's Gold, a channel where we take the periodic table and find stories no one expected. Today, element number 46. And we'll start with the biggest scientific scandal of the second half of the 20th century. Because it's this scandal that best explains why palladium isn't such a simpleton. So, what exactly happened in that beaker? Fleischmann and Pons took heavy water. This is water in which ordinary hydrogen is replaced by its isotope deuterium. They immersed a palladium electrode in it and passed an electric current. The deuterium began to be absorbed by the palladium. And then, according to them, something began to happen that shouldn't have happened according to all known laws of physics. The system was generating more heat than it was consuming electrical energy. They claimed to have detected neutrons, particles that simply can't be produced by conventional electrochemistry. Instead, they are a direct consequence of nuclear fusion. Do you understand what that would mean? Nuclear fusion is the reaction that gives the sun its light. On Earth, it can only be reproduced under conditions of monstrous temperatures and pressures. Thermonuclear installations cost billions of dollars and have been unable to achieve a positive energy balance for decades. And here we have a glass, electricity from a wall outlet, and palladium. If this were confirmed, humanity would have unlimited clean energy from water. Literally from water. Forever. The world's media went crazy. Headlines read, "Energy Revolution. Scientists have solved humanity's problem. The end of the oil age." Fears of everything, even remotely related to palladium or energy, soared. Governments around the world hastily allocated funding. Hundreds of laboratories around the world rushed to replicate the experiment. And here's where the real story begins. Most laboratories couldn't obtain the same results. Neutron flux, an inevitable consequence of nuclear fusion, is physically impossible to hide. It was either not detected at all, or was recorded at the natural background level. Each generation could not be reliably reproduced. Nuclear physicists began to speak out. The data contained methodological errors, specifically incorrect calibration of thermal measurements in electrochemical cells. The heat the authors interpreted as anomalous energy release was actually within the normal measurement uncertainty. The scientific community quickly reached a consensus. The claimed cold fusion did not exist. Fleischmann and Pons were publicly demolished. Fleischmann, a man of genuine scientific authority, earned over decades of work, essentially lost his reputation. Pons left for France and continued his research with funding from Japanese companies, but in the academic world, he became persona non grata. It was a disaster for both. But the strange thing is, the topic hasn't died. 35 years have passed since then, and the phenomenon Fleischmann and Pons attempted to describe is still being studied. It has been carefully renamed. Now they call it low-energy nuclear reactions or nuclear reactions in condensed matter. Without grandiose words, without promises of revolution. We're simply studying. In 2019, Google assembled an international team of researchers and funded a large-scale attempt to reproduce the Fleischmann-Pons effects cleanly, methodically, and with modern equipment. The results were published in the journal Nature. Conclusion. No convincing evidence of low-energy nuclear fusion was found. But This is important. The authors honestly noted that some anomalies during palladium saturation with the Ethereum cannot yet be explained within the framework of standard electrochemistry. Do you understand the point? If this were a simple error, it would have been explained and forgotten. That's how science works. They explain the error, show where exactly it occurred, and close the case. In this case, they haven't. 35 years later. And all this is due to one property of palladium, the very one that Fleischmann and Pons used in their experiment. Palladium absorbs hydrogen, a catastrophic amount of hydrogen. One volume of the metal can accommodate up to 900 volumes of hydrogen. Not 90, 900. Hydrogen atoms, the smallest in existence, seep into the plate crystal lattice and live there between its atoms, like peas dropped into punch. The metal swells slightly, but doesn't crack or disintegrate. This phenomenon is called hydrogen absorption. It's so pronounced in palladium that there are virtually no analogs in nature. And it's this property, not catalytic converters, not jewelry, not pharmaceuticals, that makes palladium a truly mysterious metal for scientists. Because when hydrogen finds itself inside the palladium crystal lattice, it's no longer quite the same hydrogen as outside. It's compressed, trapped in a fundamentally different environment. And what exactly happens to it in this state? This is a question that still hasn't been fully answered. That's why the 1989 scandal hasn't died down completely. Not because Fleischmann and Pons were right, they were apparently wrong. Because the metal itself behaves with hydrogen in such a way that researchers periodically have new questions. Before moving on, let's slow down a bit and consider what palladium is as a substance. Because its behavior with hydrogen is not a coincidence, it is a direct consequence of its physical nature. Palladium is a silvery white metal. It is similar in appearance to platinum, but noticeably lighter. Its density is about 12 grams per heap of calcium carbonate, about half that of platinum. Its melting point is 1554 degrees Celsius. For a platinum group metal, this is relatively low. Iridium, for example, melts at 2460 Celsius. Palladium is malleable. It can be rolled into sheets, drawn into wire, and processed mechanically without the risk of cracking. In this regard, it is more convenient than many of its neighbors in the platinum group. Now, about the crystal lattice. Palladium crystallizes in a face-centered cubic structure. This is the same structure as gold, copper, and nickel. The atoms are tightly packed, but between them exist so-called extoidal and tetrahedral voids, or interstitial positions. It is into these positions that hydrogen atoms are inserted. The hydrogen atom, or more precisely, the proton, because of its electron conductivity, is incredibly small. Its radius is an order of magnitude smaller than that of the palladium atom. It literally slips into the lattice and settles there. For most metals, this process ends with embrittlement and structural failure. Palladium is an exception. Its lattice is so well adapted to the presence of hydrogen that the metal expands only slightly in volume and maintains its integrity even at the saturation limit. There is another physical property that is often overlooked. Palladium is the only platinum group metal that exhibits noticeable magnetism under certain conditions. It is paramagnetic. In an external magnetic field, it becomes magnetized, but the magnetization disappears as soon as the field is removed. This is due to the peculiarities of its electron structure. Palladium has an unfilled shell with an odd electron distribution. What's this? It is this unfilled shell that largely explains its catalytic activity, its ability to hold reactant molecules on its surface and lower the barrier to chemical reactions. The electrical conductivity of palladium is approximately 10 million Siemens per meter. This is lower than that of copper, but quite sufficient for use in electronics where chemical resistance is more important than maximum conductivity. The palladium surface is another story altogether. In a finely divided state, known as palladium black, the metal acquires a huge specific surface area. It is on the surface that most catalytic reactions occur. Therefore, palladium catalysts most often use a high-pressure carrier applied as nanoparticles rather than as a monolithic metal. Examples include aluminum oxide, activated carbon, and zeolites. A few grams of palladium in this form provide a surface area comparable to several tennis courts. This is the physics behind all the stories about this metal. Remember this picture. Ductile, lightweight for a platinum metal, with an open shell and a lattice literally designed to absorb hydrogen. Everything this metal does stems from this. Incidentally, the story of palladium's discovery is like a detective story. I'll tell you about it now. August 1803, London, a private laboratory. William Haight Wollaston is not a university professor, not a court chemist, but a scientific entrepreneur. Frankly, he's already the star of our videos. His name appears in our stories quite often. So, he buys raw platinum, brought from South America. I talked about this earlier, refines it, and sells it to jewelers and industrialists. A stable business, a good income. Chemistry as commerce long before it became the norm. That day, he dissolves another batch of platinum ore in aqua regia, a mixture of concentrated nitric and hydrochloric acids that even removes gold. A standard procedure, performed hundreds of times, but something extra appears in the residue. A precipitate that shouldn't be there. Something that doesn't fit with the known chemistry of platinum. Wollaston could have written it off as contamination and moved on. He didn't. Several months of painstaking work. Dissolution, precipitation, filtration, calcination, purification again. Layer after layer, removing everything known. And in the end, at the bottom of the crucible, a tiny amount of an unfamiliar metal, silvery, ductile, similar to platinum, but not platinum. Different density, different melting point, different chemistry. A new element. And this is what it does next. This is perhaps the most unexpected thing in this whole story. Although those who watch the video about platinum know what happens next, and they won't be surprised by this fact. Wollaston doesn't publish the discovery. Wollaston begins secretly selling the new metal through intermediaries, anonymously, under the guise of new silver, in small batches without indicating the source. For several months, chemists across Europe puzzled. What is this substance? Who made it? Is it a natural metal or a synthetic compound? French chemist Richard Chenevix, working in London, purchased samples, conducted his own analysis, and published the conclusion. This is an alloy of platinum and mercury. There is no new element. Wollaston read this publication and remained silent. Only in 184 did he officially announce the discovery and named the element palladium in honor of the asteroid discovered 2 years earlier by the German astronomer Wilhelm Olbers. Pallas, in turn, is named after Athena Pallas, the goddess of wisdom and crafts. Goddess of wisdom and crafts. Knowing what this metal will do to chemistry, medicine, and energy in the next 200 years, the name seems almost prophetic. It's worth adding one detail about Wollaston that is often overlooked. In the same year, 184, he isolated another new element from the same platinum or rhodium, which I also mentioned. 2 new elements in 1 year from a single piece of metal. At the same time, he never published his method for chemically processing platinum, the technology on which his entire business was based. Only before his death in 1828 did he hand over the description to the Royal Society. 25 years of trade secrets. This is a man who understood something important long before his time. A discovery and a method are 2 different things. A discovery can be announced. A method can be held back. It is the method that provides a competitive advantage. And not only that, in his case, he also had a good capital. A sly man. He thought like the founder of a tech startup. He just lived in the early 19th century and worked with acids instead of code. Now, the obligatory information for each of our videos. Where does palladium come from on Earth? And here I don't want to tell you about neutron stars. We've discussed them in detail in our other episodes. I want to talk about something else. Something specific to palladium and what explains why there is so little of it and why it sits where it does. When the young Earth was completely molten, which continued for the first hundreds of millions of years, heavy metals sank toward the center under the influence of gravity. Iron, nickel, and along with them platinum group metals, including palladium, sank into the core. According to geochemist calculations, the Earth's core currently contains thousands of times more palladium than the entire accessible crust. It's there, at a depth of almost 3,000 kilometers. It's impossible to extract. So where did those grams of palladium come from that lie in the depths of Norilsk or South Africa? The answer? Meteorites. More precisely, the late meteorite impact hypothesis. After the Earth formed and its core separated from the mantle, meteorites continued to fall on the planet. They brought additional platinum group metals. This material didn't have time to sink. The conditions were different. It mixed with the upper layers of the mantle, and then geological processes, magmatism and tectonics, brought it closer to the surface. Palladium in the Earth's crust literally imported from an extraterrestrial source, delivered to the already formed Earth. And here's what's interesting in this context. One isotope of palladium 107, is radioactive. It has a half-life of 6.5 million years. It decays into silver 107. Over the 4 billion years that the Earth formed, all the original palladium 107 has long since decayed axa. It's gone. But the silver 107 that formed from it remains preserved in the crystals of iron meteorites. And when scientists find an anomalously high content of silver 107 in these meteorites, it's a direct trace of that long-vanished palladium 107. The magnitude of this excess can be used to calculate how many millions of years have passed since the formation of a given body. This is palladium. Silver chronometry, one of the tools used to reconstruct the chronology of the first millions of years of the solar system. The metal stored in Norilsk's industrial reserves holds information about the birth of the planets and its isotopes. This isn't poetry. It's nuclear geochronology. Okay, we figured out where Palladium came from in the Earth's crust. Now, how exactly is it extracted from that? Because that's a whole other story, and it explains a lot about both the price and the geopolitics of this metal. Palladium is almost never mined on its own. It's a byproduct, a traveling companion. Does this remind you of anyone? A character from one of our previous videos? If you guessed right, let me know in the comments. Well, it's extracted during the processing of ores mined for other purposes, primarily nickel and copper. The main source is Norilsk. The mining and metallurgical plant in the Krasnoyarsk territory is one of the largest in the world. Copper-nickel sulfide ores are mined there, and palladium, along with platinum, rhodium, and other platinum group metals, is extracted from the sludge formed during the electrolytic refining of nickel and copper. This is a complex multi-stage process. The ore is first concentrated, then smelted, then converted, and finally electrolytically processed. Only during the processing of the anode sludge is palladium produced in concentrated form. The second largest source is the Limpopo province in South Africa. Mines there operate at the renowned Bushveld complex, the world's largest igneous body rich in platinum group metals. Mining here is different. Platinum group metals are the target product from the outset, while copper and nickel are byproducts. The ore is mined underground because the ore horizons extend deep, sometimes kilometers below the surface. This requires hard work and challenging conditions. Together, Norilsk and Limpopo account for approximately 80% of global palladium production. The remaining 20% comes from Zimbabwe, Canada, the United States, Russia outside of Norilsk, and smaller deposits in other countries. Global production is approximately 220 tons per year. For comparison, gold produces over 3,000 tons per year, while palladium is 15 times less. However, the price has occasionally exceeded gold. Another source of palladium is often overlooked: secondary production. Recycling of used catalytic converters. As the number of vehicles with catalytic converters grows, and as these vehicles retire, the amount of metal available for recycling increases. Currently, recycling accounts for approximately 30% of the market supply. This is significant, and this figure is set to grow. The technology for extracting palladium from catalytic converters is not complex in concept, although it is challenging to implement. The neutralizer is crushed, the ceramic honeycomb is ground. The extracted powder is dissolved in a mixture of acids, and selective metal precipitation occurs. The yield is high, up to 95% of the original material's content. This is precisely why the theft of neutralizers, which I described earlier, makes economic sense for organized crime networks. Now let's talk about what's not mentioned in the advertising materials of mining and metallurgical companies. Because palladium mining isn't just about tons and dollars, it's also about environmental issues. In the case of Norilsk, it's one of the most dire environmental stories in the industrial world. The Norilsk combine has been operating since the 1930s. For decades, it emitted monstrous quantities of sulfur dioxide into the atmosphere, a product of sulfide ore smelting. At its peak, emissions reached million tons of sulfur dioxide per year. That's roughly the same amount as all of Canada emitted into the atmosphere during those same years. One plant. Investigation, acid rain. The vegetation within a radius of several dozen kilometers from the plant was virtually destroyed. Forests died, soils became acidic, and rivers absorbed heavy metals from the wastewater from the processing plants. In 1989, Novoselets was recognized as one of the most polluted cities in the world. The situation has improved since then, but not as dramatically as would be expected. Some obsolete facilities have been shut down. Sulfur dioxide emissions have decreased, but the soil in the surrounding area still contains heavy metal concentrations, many times higher than permissible levels. Reindeer moss, the main food source for reindeer, accumulates nickel, copper, and cobalt. The reindeer are becoming ill. The traditional reindeer herding of the indigenous peoples in the area has been virtually destroyed. In 2020, a major accident occurred. A diesel fuel spilled from a storage tank at one of the company's facilities. Approximately 21,000 tons of petroleum products leaked into the Amberna River, turning the river red for hundreds of kilometers. The cleanup effort took years. In South Africa, the environmental profile is different, but still challenging. Underground mining involves draining mine workings and pumping out water, which then carries dissolved metals. Tailings dams, vast fields of processing waste, occupy significant areas and are a source of field pollution and heavy metal filtration into groundwater. This doesn't mean mining should be abandoned. It does mean that the price of palladium in stores doesn't reflect the full cost of its production. Part of this cost is paid by nature and the people living near the mines. That's why recycling from neutralizers, industrial waste, and old electronic components makes not only economic, but also environmental sense. Metal that has already been mined and processed requires no new emissions, new tailings, dams, or new flooded rivers. 2010, Stockholm. The Royal Swedish Academy of Sciences announces the winners of the Nobel Prize in Chemistry. 3 names: Richard Heck, E. Tengigisi, and Akira Suzuki. What is the prize for? For actions involving pallid, which they developed back in the 1970s. So, more than 30 years passed from the discovery to the award. The Nobel Committee is known for taking its time, but 30 years is a long time even by its standards. Why so long? Because at first no one understood how important it was. Chemists saw an interesting laboratory tool, elegant and convenient, but nothing more. And only when pharmaceutical companies began using these reactions in the industrial synthesis of drugs did it become clear that something fundamental had happened, something without which modern medicine would simply be different, poorer, slower, less precise. Let's figure out exactly what happened, because it directly affects each of us. Organic chemistry is the assembly of molecules. You take fragments, combine them, and get substance. Drugs, dyes, plastics. All this is the result of such assembly. Sounds simple. In practice, it's excruciatingly complex. Molecules don't behave like building blocks. They don't just snap together at will. To connect two desired fragments in exactly the right place, an energy barrier must be overcome. Conditions are required: high temperatures, aggressive reagents, and there's always the risk of destroying what was painstakingly assembled. Until the 1970s, synthesizing complex molecules was precisely this: torturous. Numerous byproducts, low yields of the desired substance, expensive, slow, unpredictable. Pharmaceutical companies spent years just learning to produce a single molecule in sufficient quantities. Palladium changed the rules. The palladium atom in these reactions acts as a mediator, a molecular sworn bond, if you will. It picks up one fragment of the molecule, accepts a second, brings them together at the right point, and is released, ready for the next cycle. And yet, it isn't consumed. Clean, precise, under mild conditions with a minimum of byproducts. Richard Heck described his reaction in 1972, Niangoshi in 1977, Suzuki in 1979, Suzuki. 3 different methods built on the same principle, and all 3 are now standard tools in drug synthesis worldwide, without exaggeration. Would you like me to be more specific? Because abstract words about pharmaceuticals and synthesis are one thing, and concrete names are quite another. Paclitaxel, one of the most important anti-tumor agents used in breast, ovarian, and lung cancer. The molecules are incredibly complex, one of the most complex natural products ever worked with by synthetic chemists. Key stages of its industrial synthesis use palladium catalysis. It allows this molecule to be assembled with the desired spatial configuration and in reasonable quantities. Rivaroxaban and apixaban, modern anticoagulants taken daily by millions of people with atrial fibrillation and thrombosis after joint surgery. These drugs have replaced warfarin, a drug that requires constant blood monitoring and a strict diet. The synthesis of both involves palladium, tyrosine kinase inhibitors for various forms of cancer, new generation drugs for the treatment of HIV infection, and a number of antibiotics. Again, palladium is at key stages of synthesis. By some estimates, about a quarter of all pharmaceuticals developed since the 1990s undergo palladium catalysis stage of synthesis. A quarter. That's no small number. Incidentally, if you have a loved one taking modern drugs for cancer, hepatitis, or thrombosis, there's a real chance that these pills were synthesized with palladium unseen at the production stage. But it was involved every time. A sham. The Nobel Committee stated this bluntly in 2010. Palladium cross-coupling reactions have allowed organic chemists to construct complex molecules with a precision and efficiency that was previously simply unattainable, Bilsonity unattainable. This has changed chemistry in the same way that the advent of new surgical instruments changes surgery. Not a revolution for the sake of revolution, but an expansion of what is possible. The 30 years between the discovery and the award reflect the committee's sluggishness. That's the time it took the world to understand the scale of what had happened. Now, as all about money. But where would we be without it? Because without it, the picture is incomplete, and you know that. Annual global palladium production is approximately 220 tons. Demand has consistently exceeded supply in recent decades, primarily due to stricter environmental standards for automobiles worldwide. We've discussed catalytic converters and how they work in detail in previous issues. We won't repeat ourselves. We'll just say one thing. The automotive industry consumes the vast majority of the world's palladium, and this directly determines the price. In 2010, palladium became more expensive than gold for the first time in history. The price of a troy ounce, about 31 grams, exceeded $2,700 bars. Gold was then worth about $1,600 per ounce. A metal most people have never heard of has overtaken a metal that has been a measure of wealth for millennia. And here begins the story of how one of the world's largest automakers made a $1 billion mistake. It's a cautionary tale, especially for those who believe large corporations with thousands of analysts can predict the markets. Well, most of the time, of course, but there are also failures. It's the late 1990s. Supplies of pallade from Russia are unpredictable. Here's the thing. In the Soviet Union, pallade production and export were completely secret. The state was accumulating strategic reserves. No one outside a very small circle knew exactly how much. After the country's collapse, the new Russia inherited these reserves and, in the 1990s, periodically released them onto the world market, sharply driving down prices, their prices. when the next release would occur and in what volume was impossible to predict. Reserve data remained a state secret. For buyers at major automobile companies, this was a constant headache. Planning production without knowing the price of a key raw material 6 months from now is a very uncomfortable situation. General Motors decided to hedge its bets. The company purchased large strategic reserves of palladium at high prices in case of a shortage. The logic is clear. Better to overpay now than to halt production later. Soon after, prices collapsed. Russian supplies stabilized. Hidden reserves, the existence of which no one had suspected, came to the market. General Motors was left with a huge amount of expensive metal, which was now significantly cheaper. Losses from this deal are estimated at approximately $1 billion. One metal, one incorrect forecast. $1 billion in losses for one of the largest corporations on the planet. If you think about it, this demonstrates something important about the structure of the palladium market. When supply is concentrated in two places, Norilsk and the Limpopo province in South Africa, they together account for approximately 80% of global production. And when information about actual reserves is classified, the entire market lives in conditions of chronic uncertainty. Even corporations with thousands of analysts and multi-billion-dollar budgets are off by $1 billion because the information simply doesn't exist. It can't be bought at any price. It's appropriate here to address a question that automotive industry analysts have been asking for a long time, and which became especially prominent during the price peaks of 2020. If palladium is more expensive than gold, why not replace it with platinum? Platinum is also a catalytic converter. Platinum is also used in catalysts. In diesel engines, it is the primary metal. Why not switch to platinum in gasoline catalysts as well? The idea sounds reasonable on paper, but in practice, things are more complicated. Palladium and platinum are related metals, but not interchangeable. In gasoline engine catalysts, palladium is more effective under typical engine conditions at higher exhaust gas temperatures and with richer fuel-air mixtures and with richers. Platinum is less active under the same conditions. To achieve similar exhaust cleaning efficiency, it would be necessary to either increase the amount of platinum, which would partially offset the price savings, or significantly redesign the catalyst. This is precisely what engineers at leading automakers and catalytic converter manufacturers have been working on since the late 2010s. BASF, Johnson Matthey, and Umicore, among the world's largest automotive catalytic converter manufacturers, have publicly reported on ongoing developments to partially replace palladium with platinum in gasoline catalysts. The results are still cautious. Partial replacement is possible. Complete replacement is technically significantly more difficult. Firstly, platinum performs worse during the so-called cool down, the first few minutes of engine operation, when the catalyst has not yet reached operating temperature. It is during this period that a significant portion of harmful emissions occurs, and palladium performs significantly better here. Secondly, the switch between metals requires significant investment in retooling production lines. The automotive industry is characterized by rigorous development and production cycles. Simply replacing the metal in an already certified catalytic converter is impossible. New certification, new testing, and new documentation are required. This takes time and money. Thirdly, and this is often overlooked, platinum is also mined primarily in the same geographic locations, South Africa and Russia. A large-scale switch from palladium to platinum would not solve the problem of geopolitical vulnerability in the supply chain. It would simply transfer it from one metal to another. Nevertheless, progress is being made. Some manufacturers have already introduced catalytic converters with a higher proportion of platinum in the metal mixture. As technology improves, this proportion may increase, but the complete replacement of palladium with platinum in gasoline catalytic converters, if it occurs at all, is a matter for the next 10-20 years, not tomorrow. And here a curious market paradox arises. The very fact of active research into replacing palladium with platinum puts pressure on the price of palladium and increases demand for platinum. The market trades not only what is available now, but also what may happen in the future. Rumors of progress in creating platinum catalysts for gasoline engines immediately affect the prices of both metals. Such is the feedback loop between the laboratory, the factory, the stock exchange, and geopolitics. But let's return to science, because there's another story related to palladium and hydrogen. It's far less scandalous than the 1989 event, but far more practical and far more relevant right now. Hydrogen energy. The Toyota Mira, the Hyundai Nex, hydrogen buses in European cities. This is no longer the future. It's the present, albeit still on a limited scale. Hydrogen burns, producing only water. No carbon dioxide, no smog. An ideal fuel from an environmental perspective, provided we learn how to store and transport it safely. Storage is the main problem. Hydrogen takes up a huge volume under normal conditions. To make it compact, it would need to be either compressed to 700 atmospheres or cooled to negative 53 degrees Celsius using palladium. Both options are technically challenging and carry certain risks. But what if hydrogen were stored directly in the metal, absorbed and released as needed as? This is where palladium proves to be a model material, ideal in its properties, but too expensive for mass production. Therefore, it is used as a benchmark, and the mechanism of hydrogen absorption and release is being studied in order to subsequently create cheaper analogs from other metals and alloys. Nickel alloys, lanthanum-based alloys, all of this is developing in part because the mechanism was first understood using palladium. Furthermore, palladium membranes are already used in industry for hydrogen purification. Only hydrogen passes through a palladium membrane when heated. No other gas can physically leak through the metal's crystal lattice. This allows for the production of high-purity hydrogen, which is critical for semiconductor manufacturing and hydrogen fuel cells. Here's a curious paradox. A metal that seemed firmly tied to the era of the internal combustion engine may well be in demand in the next energy system, only in different roles. This incidentally says something important about how technological development works in general, but I'll discuss that in the final section. Incidentally, there's another aspect of the hydrogen topic that's worth discussing separately: palladium hydrogen sensors. Hydrogen burns in a concentration range from 4 to 75% air. This is a very broad range, wider than most flammable gases. A leak must be detected long before the concentration reaches dangerous levels. This means a sensitive sensor that responds to trace amounts is needed. Palladium sensors utilize the same property of the metal, selective hydrogen absorption. When hydrogen comes into contact with a palladium sensor element, its electrical resistance changes. This signal is recorded and alerts to a leak long before the concentration becomes dangerous. Such sensors are installed at hydrogen filling stations, industrial facilities, and even on hydrogen-powered vehicles themselves. As the hydrogen infrastructure grows, their number will only increase. And again, Palladium is at the center. Quiet, unnoticed, yet critically important. Okay, now let's talk about palladium's lesser-known uses. Dentistry. Palladium-based alloys, typically combined with silver, copper, and other metals, are used for dental crowns, bridges, and inlays. The metal is biocompatible, hypoallergenic for most patients, resistant to corrosion in the aggressive oral environment, and has suitable mechanical properties for chewing. In Japan, palladium dental alloys were incredibly popular from the 1970s to the 1990s. At certain points, the country consumed approximately 25% of global palladium production, specifically for dental purposes. It's hard to imagine, but a quarter of the world's palladium went into the dental crowns of Japanese patients. When global metal prices soared in the late 1990s, Japanese dentistry found itself in a difficult situation. The cost of crowns skyrocketed. Patients thought twice before agreeing to treatment. There were stories of people bringing in their old crowns to be melted down because the metal in them was worth more than the dentist's labor. This is not an anecdote. It is a documented practice of that period. Electronics. Multi-layer ceramic capacitors components, of which a modern smartphone contains between 500 and 1,000 and even more, in automotive electronics were historically produced using palladium-silver alloys as electrodes. The industry has largely switched to cheaper nickel, but in highly reliable applications, avionics, medical implants, military systems, palladium remains essential where the cost of component failure is unacceptable. When it comes to aircraft control systems or pacemakers, no one skims on metal to reduce the costs by a few cents. Jewelry. Pure palladium is a white metal with a durable luster that doesn't darken over time and doesn't require additional rhodium plating, unlike white gold. It's approximately half the weight of platinum with a similar appearance. It's hypoallergenic, which is important for those with sensitive skin, of which there are many among those who wear jewelry regularly. In 2009, the UK became the first country in the world to officially include palladium in its national assay system. Since then, palladium wedding rings have been quite common in several European markets. Not exotic, but a normal choice. Now about medicine. Not about pharmaceuticals, which we already discussed in the previous section, but about something else. About what happens not in a chemistry flask, but right inside the human body. The isotope palladium-103 is an artificially created radioactive isotope with a half-life of approximately 17 days. It is used in brachytherapy, a treatment for malignant tumors in which a radiation source is placed directly inside or adjacent to the tumor. The idea is to irradiate cancer cells with a high dose while minimizing damage to surrounding healthy tissue. This fundamentally distinguishes brachytherapy from external beam radiation, which targets healthy tissue en route to the tumor. The seeds contain palladium-103. These tiny cylinders, approximately 8 millimeters in diameter and 4.5 millimeters in length, are implanted directly into the tumor tissue. This method is widely used in early-stage prostate cancer, one of the most in. Over 17 days, the radiation source gradually burns out. In most cases, there is no need to remove the seeds. They remain in the body permanently, causing no harm after their activity has been exhausted. This creates an interesting and somewhat paradoxical picture. Palladium plays a role in the fight against cancer in two completely different capacities. As a catalyst in the synthesis of anti-cancer drugs, which we discussed in the previous section, and as a direct source of therapeutic radiation within the tumor itself, which we are discussing now. These are two different mechanisms, two different physical principles. One element in the periodic table, number 46. Now, a discussion rarely heard in stories about platinum group metals. What happens to palladium after it enters the environment? Not at the mining stage. We've already discussed Norilsk. But during use and wear. The main route for palladium to enter the biosphere today is through exhaust gases and the wear of catalytic converters. Catalytic converters operate under harsh conditions, high temperatures, mechanical vibrations, and an aggressive chemical environment. Even though palladium is coated with nanoparticles and held there quite firmly, some of these particles are still released during operation. A very small fraction of a gram over the entire service life of a converter. But multiplied by hundreds of millions of cars worldwide, this is no small figure. Palladium nanoparticles settle on the road surface and are washed away by rain into the soil and water bodies. Concentrations in roadside soils along busy highways, particularly in cities, have increased tenfold over the past 30 years compared to pre-motor vehicle levels. In some measurements conducted near major transport hubs in Europe, palladium concentrations in roadside soil were comparable to concentrations of traditionally monitored pollutants such as lead and cadmium. What happens to these nanoparticles in soil and water? This is an area of active scientific research, and the answers are not yet complete. Following is known. Platinum group metals in general and palladium in particular are highly chemically stable. They dissolve slowly in soil solutions, but in the presence of organic acids released by plant roots and soil microorganisms, solubility increases, making the metal available for uptake by plants. Plants growing along roadsides show elevated palladium levels in their tissues. This has been documented for roadside grasses and shrubs in several European studies. What happens next when these plants are eaten by herbivores is less well understood. But the basic logic of bioaccumulation means that the metal potentially moves up the food chain. For aquatic ecosystems, the picture is also ambiguous. Elevated concentrations of palladium have been recorded in river sediments near large cities. Some aquatic organisms, including bivalves and crustaceans, accumulate platinum group metals from the water. The toxicity of palladium to aquatic organisms has been poorly studied, but experiments show that at certain concentrations, palladium nanoparticles inhibit algae growth and disrupt fish behavior. An important caveat: metal nanoparticles behave differently than ions of the same metal in solution. Particle size determines their bioavailability, their ability to penetrate cell membranes, and the nature of their interactions with biological molecules. This makes risk assessment particularly challenging. Standard toxicological methods developed for ionic metals are only partially applicable to nanoparticles. So far, the situation has not posed the threat of an acute environmental crisis. Concentrations remain below acute toxicity thresholds in most cases, but a steady increase in palladium concentrations in urban ecosystems as the number of vehicles with neutralizers increases has been documented and continues. There's another story related to palladium and source measurements, and it's far less well known than the 1989 scandal. Those who watched our episode about cadmium already know the ending. There, we discussed in detail how the cadmium red spectral line served as the international optical standard of the meter for 33 years. But that story has a prequel, and it involves palladium. In the late 10th and early 20th centuries, spectroscopy of platinum group metals was one of the most precise areas of measurement physics. Scientists competed to accurately measure the spectral lines of platinum, palladium, rhodium, and iridium. It was this painstaking, methodical work without obvious practical application that convinced the scientific community that the spectral lines of metals are sufficiently stable and reproducible to serve as length standards. An atom is the same anywhere on the planet, in any laboratory, at any time, unlike a metal rod in an underground vault in Sèvres. Albert Michelson, the same one who in 1887, together with Morley, demonstrated that the speed of light is independent of the Earth's motion, and who in 1907 became the first American citizen to receive the Nobel Prize in Physics. In his precision interferometric measurements, he actively worked with the spectral lines of platinum group metals. It was his work that transformed the idea of an atomic standard from theoretically attractive to practically feasible. Palladium didn't become the final standard. That turned out to be cadmium, as we've already discussed. But palladium was part of the scientific tradition, without which the atomic standard of length would not have been accepted as it was. A quiet contribution, as is often the case with this metal. Incidentally, speaking of standards and measurements, the meter today is neither a metal pond nor a spectral line. The modern definition of the meter is as follows. 1 meter is the distance light travels in a vacuum in 1290,790,458 diites of a second, spar of a second. That is, the definition of the meter is based on the speed of light, 292,000 meters per second. A fixed physical constant, unchanging at any point in the universe. This path from a metal rod to the spectral lines of atoms, and then to the speed of light, became possible in part thanks to the painstaking spectroscopic work with platinum group metals, in which palladium was involved. What do you think this metal remembers? It sounds strange and a bit philosophical. Metal doesn't think, doesn't remember. But isotopes, that's a whole different story. Isotopes truly do store information, and in the case of palladium, this turns out to be the key to several stories that simply couldn't be told otherwise. We already discussed palladium-107 in part 1 and how its decay into silver-107 allows us to date the first millions of years of the solar system using palladium-silver chronometry. But palladium has another isotopic history, and it's not connected to meteorites or the birth of planets. It's connected to the oceans, the living oceans that existed on Earth tens and hundreds of thousands of years ago, long before the advent of humans, but are already quite recognizable by their chemistry. In seawater, palladium is present in trace amounts ranging from 5 to 20 picograms per liter. A picogram is 1/trillionth of a gram. This is so small that it only became technically possible to measure it in recent decades with the advent of high-resolution mass spectrometry. But it is precisely because of these trace concentrations, that palladium's behavior in the ocean is particularly informative. In surface waters, where active photosynthesis occurs and biological productivity is high, palladium is actively absorbed by marine organisms, plankton, and algae. Concentrations in the surface layer are relatively low. In deep waters, where dead organisms sink and organic matter decomposes slowly, palladium is released, and its concentration is higher. This behavior is recorded in marine sediments on the ocean floor, layer by layer, millennia after millennia. The isotopic composition of palladium in sediments of different ages reflects the state of the ocean during different climatic eras. How active was photosynthesis? How did water circulation change? What did the ocean look like during the last glacial maximum 20,000 years ago? In Palladium, silver chronometry works with it meteorites and the first million years of the solar system. Isotopic analysis of a palladium in marine sediments works on a different timescale, tens and hundreds of thousands of years. Two different tools, or one element. Atomic number 46. This area of research is relatively new. Methods are rapidly evolving, but scientists are already using palladium isotopes in sediments as a marker of historical changes in deep-sea ecosystems. Every metal in the periodic table is not just a substance, it is simultaneously a sensor, a chronicle, and a tool. Palladium is one of the most eloquent examples. So where are we with palladium right now? The palladium market is structurally vulnerable. Norilsk and the Limpo province account for approximately 80% of global production. This means that the entire metals industry dependent on it lives under chronic geopolitical risk. We saw this with the unpredictable Russian supplies in the 1990s. We see it every time something happens in Norilsk, and global prices react instantly. At the same time, demand is changing. Electric vehicles are gradually replacing internal combustion engines. In the long term, this will reduce the need for palladium in neutralizers. At the same time, hydrogen energy is growing, where palladium is in demand in other roles. Nuclear medicine using palladium-103 is expanding. Highly reliable electronics are developing, where palladium has no substitute yet. Where will all this go in 28, 30 years? Honestly, no one knows. Anyone who tells you they know is either wrong or misleading. The palladium market is inherently unpredictable. There are too many independent variables, too concentrated a supply, and data on actual reserves is too classified. But one thing is certain in the 220 years since its discovery, palladium has never been unnecessary. Every era has found a use for it. Sometimes unexpected, sometimes scandalous, sometimes life-saving in a literal medical sense. All the important stories involving palladium have one thing in common. None of them were planned. Wollaston didn't plan to discover a new element. He was testing the quality of platinum ore. Fleischmann and Voss didn't plan to cause the biggest scientific scandal of the 20th century. They were studying electrochemistry. Richard Heck didn't plan to change pharmaceuticals. He studied organic reactions involving transition metals. The scientist who discovered that the isotopic composition of palladium in marine sediments reflects climate history. He studied ocean geochemistry without thinking that he was creating a new tool for paleoclimatology. Every time, first observation, then understanding, then application. Never the other way around. This contradicts how scientific progress is usually imagined. We think that society first formulates a problem. We need a cure for cancer. We need clean energy. And then scientists go and solve it. In fact, more and more often, a different mechanism is at work. Scientists study something because it is interesting in itself, and only later, sometimes 30 years later, as in the case of the Heck reaction, does it turn out that it was the answer to a question no one had yet asked. Palladium is a perfect example of this principle. Finally, a detail I deliberately left for last. The Wollaston Medal has been awarded in Great Britain since 1831. It is the highest award of the Geological Society of London. It is named after the man who discovered palladium iridium. He kept his method secret for 25 years, sold his discoveries through intermediaries, and bequeathed a significant portion of his fortune to the advancement of science. The medal is still awarded to this day, almost 200 years later. Among the laureates over the years are Charles Lyell, one of the founders of modern geology, Louis Agassiz, who discovered the ice ages, and William Smith, who created the first geological map of Great Britain. In the 20th and 21st centuries, dozens of outstanding geologists and geochemists have been awarded a medal that arrived on Earth in meteorites after its formation, which stores information about the birth of the solar system and the climate of ancient oceans in its isotopes, which is worth more than gold, and is the reason car parts are stolen, which saves lives through medicine, and brachytheters, which allowed us to understand how to assemble complex molecules and thereby change medicine, which still keeps part of the scientific community on edge due to its strange behavior with hydrogen. That's what palladium is. Not just an element number 46 on the table, but a metal that repeatedly appears where something important is happening and yet remains virtually invisible to most people. Perhaps this is its main properties. Friends, let me know in the comments what surprised you most in today's video. If you'd like more on the neighboring platinum group metals ruthenium, osmium, and iridium, let me know in the comments. Everyone has their own story, completely unexpected. Thank you for your feedback. I read all the comments. They help our channel become better. See you on Fool's Gold, the channel where we take the periodic table and find stories no one expected to find there. See you soon.